This is the second video on intermolecular forces. This time we're talking about dipole-dipole forces and hydrogen bonding. And these are getting a little bit stronger than dispersion. So how do we distinguish when we have those types of forces? Well, first of all, what is a dipole? A dipole is a molecule that has a slightly negative end and a slightly positive end. And so I've got a couple examples here. I'm going to draw H2S. This looks kind of like water, except for it's got sulfur. And this bond right here between the hydrogen and sulfur is polar. That's a polar bond. And so this end, the sulfur end, is slightly, it's not positive, it's slightly negative, and the hydrogen end is slightly positive. So this is a dipole. It's got two ends, and it's going to attract the opposite end of a neighboring molecule. And so if you were to show those forces, you would draw a second molecule, and then they would be attracting the opposite ends. The last little molecule, the carbon, has three hydrogens, and this is a tetrahedral shape. However, I do have one bond that's a little bit different, and this end here is going to be a slightly polar bond, and so this molecule would be slightly negative on this end and slightly positive on that end. So that is also a dipole, and so we would expect dipole-dipole forces with that substance. Now, let's see if we can predict which one is more polar and would have a stronger dipole force. Well, we've got hydrogen and chlorine. Both chlorine and bromine are a little bit electronegative, but the electronegativity of chlorine is a little bit greater. This is going to be a greater polar bond. Also, chlorine is smaller, and so I would predict that this would have the greater dipole-dipole forces. Now, what is hydrogen bonding? Now, don't think hydrogen bonding is what you have inside of a water molecule. That is the intramolecular force. Hydrogen bonding, and this is a definition you need to memorize, is this. It's the attraction between a hydrogen bonded to an F over N and the F over N of another molecule. So our hydrogen has to be bonded to one of those three atoms. I like to use this little phrase, hold the phone, to help you remember what that hydrogen has to be holding onto an F over N. So I'll show you some examples. These are the strongest forces. These are very, very strong forces. So let's take a look at water. Does the hydrogen, is it bonded to an F over N? It is. And so what this is going to do is, let me draw another water molecule. And this is how we would show the hydrogen bonding. It's between the hydrogen bonded to an O, F, or N, and the O, F, or N of another molecule. And so we would draw a dotted line showing the hydrogen bonding. Okay, next door I've got an ammonia molecule. Is the hydrogen bonded to an F over N? It is. So we have hydrogen bonding here as well. Also with HF, we would show, let's do another molecule here. I have HF, and I'll draw a couple more. And let's draw some hydrogen bonding. So make sure you go from the hydrogen to the fluorine. And then this one would be attracted here. Okay? And the more hydrogens bonding, the stronger the force. Now, I've got a molecule up here. Take a look at this one. I do have hydrogen and I do have oxygen, but is there hydrogen bonding? Is my hydrogen bonded to an F over N? It's not. It's bonded to a carbon. And so there is not hydrogen bonding in this molecule. Now, hydrogen bonding is the strongest force. Then dipole-dipole, and then London dispersion forces are the weakest. Let's identify all of the IMFs present. Now, this takes a little practice, so let's just get started. First of all, every molecule or atom does have London dispersion forces. So I'm going to go ahead and write that down. I've got London dispersion, London dispersion, London dispersion. Wait a minute, what is this next one? Sodium sulfate, what is that? This is an ionic compound. How did that get in there? Okay, I just wanted to make sure that you're aware of ionic compounds. And so that is a totally different structure. There's a crystal lattice IMFs really don't apply in this case. And then hydrogen, we've got London dispersion forces. All right, so I've got 4 molecules. What else do we see? Where do we have a dipole? Well, that first molecule, that methane, is tetrahedral and perfectly symmetrical, nonpolar bonds. We don't have anything else. No hydrogen bonding. The next one is, and I'll just draw it again here, this is kind of like methane, where we've yanked off one of those hydrogens and put a chlorine there. So this is now a dipole, and so we have dipole-dipole forces here. All right, and then on the next molecule, methanol, we've got carbon, and this time I'm going to just erase it here. And we've got not another hydrogen there, but look what we have on here. We've got an OH. And guess what we're going to have here? This is also a dipole. And then we also have, check that out, hydrogen bonding. Okay, so we have all 3 forces on the methanol. And then down to the little hydrogen, all we have is London dispersion forces. It's not a dipole. Now this takes practice. Lots and lots of molecules, identifying your intermolecular forces.